I'll be presenting about autonomous systems and its development with model-based system engineering. I'll start with the mega trend, adding autonomy. It is followed by a brief introduction about model-based system engineering and its necessity for complex system development. What all the MATLAB solutions are available for each stage in the development of autonomous systems. And we will also have a look at MATLAB support mechanism for model-based system engineering and autonomous system development. It will be followed by an informative session about upcoming events of CES Dubai. Okay, we are good to go. When you hear about robotics, you may first think of robot manipulators or mobile robots in factories. Robotics has grown beyond that. Adding autonomy is a trend happening across many industries. You will find defense contractors building next generation autonomous underwater vehicles, autonomous drones, unmanned ground vehicles, UAVs, autonomous vessels, etc. You can also find traditional big machine makers in construction, mining, and agriculture actively investing in autonomous capabilities. And in the advanced air mobility trend, there are also commercial aircraft makers adopting similar sensing and automation technologies from robotics into their aircrafts. The development of any autonomous system requires collaboration of interdisciplinary teams. One way of thinking about the landscape is using the emerging mission engineering perspective. Let's consider the example of autonomous underwater vehicle development. At the component level, engineers and scientists might be developing something like sections of a hull of a modular underwater vehicle. At the system level, system engineers and managers might be interested in system level performance of the vehicle in terms of its specifications measured against a set of requirements. This could be physical specification or performance specification. And that might connect to a system of systems level of mission engineering and like what DARPA has been promoting in terms of mosaic warfare concept. How does this fit into a total package and what tiles are needed to connect it into a bigger picture? And then there is the mission level, which is ultimately the most important driving force in this picture. The digital engineering vision is to help the stakeholders at this level to get answers to questions like how does swapping this component for another impact the mission, or how long does this vehicle's power need to last for our mission to be successful, and testing it out on a digital model before moving to expensive or long lead time equipment or deploying it in the field. Answering these questions with a reasonable degree of confidence with models at the foundation built up using digital engineering is where mission engineering has the potential to be the most powerful. I think MathWorks can help connecting the stakeholders across all levels here. MathWorks tools can provide a common integration environment for autonomous system development, like model-based system engineering, multi-domain platform and system model, autonomous algorithm development, and environment and sensor modeling, to name a few. Let's consider the model-based product development process. Autonomous system development will require a total system engineering approach with multi-domain systems modeling and comprehensive information continuity, like a digital thread tying all the processes together. MBSE, that's model-based system engineering, is a formalized application of modeling to support system requirements, analysis, design, validation, and verification activities, beginning in the conceptual design phase and continuing throughout the development and later in the life cycle phases. MBSE methodology uses models to represent and analyze complex systems. It is done by using models to capture the system's requirement, design, behavior, cost, risk, and other aspects. There are several system engineering approaches that can be used to support MBSE. For example, agile system engineering, system of systems engineering, modular open systems approach, V model, etc. What you're seeing here is a V model. It adds a testing phase for each development stage, which helps to ensure the quality. Model-based design is a systematic. Sorry, some interruption happened here. Model-based design is a systematic use of models throughout the development process that improves how you deliver complex systems. Why is MBSE necessary for autonomous systems? Now, more than ever, the MBOC approach is necessary to address the complex, multidisciplinary, multi-domain process of autonomous system development, which most meticulously orchestrate mechanical, electrical, electronic, software, and controls engineering. With MBSE approach, engineers can capture the needed complexity and behaviors of advanced real-time features for an autonomous systems like robotics, mobility services, mapping systems, smart body structure, vision and detection, user interface, communications between the vehicles, machine learning, etc. MATLAB enables the development teams to understand an area of interest or concern and provide unambiguous communication among the interested parties. Model-based design. We describe model-based design as a systematic use of models throughout the development process. And there are two major components. First one is modeling and then automation. The modeling includes simulation and analysis. It helps you to try out new ideas and a fast repeatable test. Next is automation. It includes coding and verification. It helps you to take out manual steps and reduce human errors. MathWorks is a one-stop shop for model-based system engineering. MATLAB, Simulink, and System Composer together create a single environment for creating descriptive architecture models that seamlessly bridge into detailed implementation models. The connected environment ensures items across the architecture and design worlds stay in sync. The system engineers can establish a digital thread to navigate between system requirements, architecture models, implementation models, and embedded software. We will see the details of the digital thread in upcoming slides. Here comes the workflow of different types of autonomous system. First one is a workflow of a manipulator or the robot arm or the cobot development. Next is a workflow of a mobile robot or autonomous mobility development. And there comes the autonomous underwater or the surface vehicle development workflow. And next is UAV or drone or autonomous flight development workflow. Of all these four workflows, did you notice something? If yes, you've got 10 seconds to post it in the chat. So where is the difference? It's mainly in the platform or the sensors and the application environment. Basic workflow remains the same. Now let's consider some of the common challenges in each phase of this workflow. If you're working in autonomous system development field, I have few questions to you. How do you ensure traceability from system requirements to code? How do you model physical interaction and system dynamics? How do you visualize and analyze the data from robots? Do you have any compliance or standards like DO 178C, ISO 26262, or any other standards to meet? What is the TRL of your system according to the technology readiness levels? How do you do hardware in the loop test? How do you convert different code formats? And finally, how do you evaluate the impact of a requirement change to the design, especially the one found during the system testing? Developing autonomous systems with MBSE approach helps you to manage this kind of system complexity. As these advanced systems become more interconnected and complex, MATLAB, Simulink, System Composer, and Requirement Toolbox together create a single environment for creating descriptive architecture models that seamlessly bridge into detailed implementation models. You can seamlessly link the requirements to architecture, architecture to design, and design to code. The connected environment ensures that items across architecture and the design world stay in sync. We heard the term digital thread many times. What does it mean? The advantage of unified environment is the stakeholder needs are converted to requirements and use cases, which in turn aid in creating a system architecture and hence a digital thread. It will facilitate analysis and execution, simplifies complexity, enables implementation, and seamless verification and validation. The system engineers can establish a digital thread to navigate between system requirements, architecture models, implementation models, and embedded software. Now let's see how does this digital thread looks in a real environment, a real development process. Digital thread connects requirements, architectures, architecture views, operational scenarios, variance management, detailed design, verification and validation, and code generation. This slide shows the MATLAB solutions for each phase of a UAV development workflow. I would like to emphasize, now you can see it includes the following: the system definition, platform design, AI or the autonomy design, the verification and validation, 3D scenario simulations, connecting to the robot, and implementation to hardware. So I would like to emphasize here that this webinar will be focused on system engineering and verification and validation. We have more, like what Cicely has mentioned, we have more webinars in the autonomous system series covering system design and dynamics modeling from desktop environment to HIL, SIL, and PIL setups, and autonomy algorithm design of autonomous systems covering localization, planning, sensor fusion, and control to hardware development. This will take place in November and December respectively, so stay tuned. So let's first consider system engineering. Madhus introduced System Composer with 2019 version. So it's a model-based system engineering tool for you to architect your systems before you design and implement them. It helps you by connecting your descriptive model in System Composer to your design models in Simulink. And with this, you can separate functional, logical, and physical layers in your architecture, perform trade studies, associate requirements to your architecture model elements for traceability and validation, and run simulations to verify the performance of your system. System Composer helps to bridge the gap between system engineers and engineering specialists between requirements and detailed design. Here is an example of defining system architecture for a UAV. Now, in the beginning of the workflow, the system architecture will be designed based on the requirements definitions. With the System Composer, you can author the system architecture, allocate requirements to architecture model components for traceability, and investigate your design. So here you can see the top level components of a small UAV model. It has propulsion, flight computer, flight support components, payload, airframe, supervisory computer, etc. And it has more components inside. We'll consider this example. We'll see this example in the following slides. A typical challenge is that there's often a need to port the architecture design between different tool environments. But with System Composer, you can integrate the model-based system engineering and software architecture modeling with Simulink workflow for model-based design, allowing for streamlined processes which maintains traceability. The slide is about the requirement toolbox. With requirement toolbox, you can author, link, and validate the requirements for designs and test. You can define your requirements using rich text or custom attributes and keywords. You can also import and view requirements from other sources such as IBM DOS Next, Microsoft Word, or Microsoft Excel. It also supports the requirement interchange format RIC-IF to exchange requirements with the tools supporting that format such as Siemens Polarion, ALM, or JAMA Connect. You can also specify formal requirements using logical expressions with the requirements table block in Simulink. You can use the requirements perspective to view, author, and organize the requirements directly in Simulink, System Composer, or Stateflow editors. You can analyze the requirements coverage, identify the gaps in implementation and testing, missing requirements, and design errors. You can also create a traceability diagram to visualize and navigate to the linked items. It also helps you to create configurable reports that include links, change information, and implementation and verification status. Finally, it helps you to trace requirements to MATLAB code and test. This is this example uses requirements toolbox, Simulink, and System Composer. This example shows, this is the example I have shown in the previous slide. It basically shows how to use System Composer to set up the architecture for a small unmanned aerial vehicle composed of 6 top-level components. You can learn how to refine your architecture design by authorizing the interfaces, inspect link textual requirements, define profiles, stereotypes, etc. Each top-level component is decomposed into its subcomponents. So I'm just navigating through the hierarchy to view the composition of each component. The root component, it has input. So now we are seeing the what is the subcomponent in the airframe. Next, what is there in the supervisory computer. We can also define interfaces for domain-specific data between the connections. The information shared between two ports defined by an interface element property values further enhances the specifications. So if you click on the GS commands, we can see the more details about that one below. So it opens up the interfaces window and we can see the type, dimensions, units, complexity, minimum, maximum value, descriptions, etc. Now let's have a look at the requirements linked to each components. So once we right click and click on the requirements, we can see the linked requirements if there is any. So let's click on that requirement and it will open up the requirements editor. We can also open the requirements tab by clicking on the bottom right part that we can use using the ender perspective requirements. It will open the requirements like this. Then let it expand. So once we open, we can see the components to which the requirements are linked. It is implemented like that. It will appear. Now let's try to trace it back from the requirements to the model. So this is 1.2 is not linked, so it is not highlighted in the model. Let's click on the range. So it is linked to the propulsion component. Next is emergency power, fuel, lights. It's linked to flight support components. So you can also, if you go to the model, you can also see it's being highlighted there. So I've just linked one requirement to the supervisory computer. It was not linked. For that, I have selected the requirement first, and then I have right clicked on the component and then requirements, then link to the selection in the requirement browser. So it has just linked that requirement to this component. Now let's have a look at the profiles and the stereotypes. So just before that, we will consider the carrying capacity. So for this aircraft, the condition is that the aircraft shall be able to carry up to 2.2 kilogram of payload. So let's see whether this model meets that requirement or not. So first we'll go to the profile editor. And then for this one, there is a profile called UAV component. It has three stereotype: onboard element, RF connector, RF wiring, etc. So this stereotype basically helps you to add the metadata related to that component. So for example, for onboard element here, mass, power, and RF harness length has been added. For the RF connected, it's only connected type. So you can see the minimum value, maximum value, the units, the data type, etc. has been added to each stereotype. Now let's go to the analysis model. So it will create an instance model for this architecture model by flattening out all the reference models. So we are checking the total mass of this model. So yeah, the iteration is from bottom up, and let's instantiate. Now I'll click on the analyze part. So before going to the analyze, we can see for each component, based on the metadata added for each stereotype, it will list here the mass being added for each one. Now we want to see whether the payload is less than or equal to 2.2. So once analyzed, it will show the total weight is 15.462 kilogram. Now let's have a look at the payload. It is 1.317. So it is less than 2.2 kilogram. In this way, we can analyze, we can run the static analysis on your system, create an analysis model from your architecture model. So it's a tree of instances generated from the elements of the architecture model in which all reference models are flattened out and all variants are resolved. So the analysis function iterates through the model elements in the bottom-up approach and assigning the mass property of each components as a sum of the mass properties of its components. The overall weight of the system is assigned to the mass property on the top level. That's what we have seen it as 15.462. Let's move on to the platform design. So again, I would like to add that more information on the autonomous system stages like the platform design, autonomy algorithm development, 3D simulation, connect and deploy to hardware. It will be covered in detail in our upcoming webinar series. Hence, I have included limited information, and it includes simple demos. So in this slide, you can see like the typical the MathWorks tools solutions for the platform design. So it supports the physical modeling with Simscape and its related tools like Simscape multibody, Simscape electrical, then Simulink control design, robust control toolbox, aerospace block set, Stateflow, etc. So this is a demo video of pick and place manipulation applications, which is one of the biggest uses of collaborative robots. It looks simple for you to pick them up, but it's not trivial for the robot to pick an object and place them at a goal location. Robotic arm used here is the Kinova robot manipulator, one of the collaborative robots. It has a stereo camera mounted on its wrist. Let's take a closer look at how we design this pick and place manipulation application using MATLAB and Simulink. To start developing a robotic application, you'll need the platform of the robot. The platform design in general involves mechanical system, actuators, and the environment model that the robot interacts with. Do we need to model all of them? Well, it depends on your application. If you're a control engineer, you may need to model mechanical systems and actuators. In Simulink, you can create high fidelity robot models and mechanical system by connecting to CAD models such as SolidWorks here. This is just one example of the importance of having tools that has interoperability with other tools seamlessly. And here you see an example of how we can size joint actuators and test motor requirement to lift up your target payload. Simulation become more important in development process of autonomous system. For many workflows like testing, training AI systems, and debugging, the physical system is replaced with the simulation. The simulation but engineers will need to rebuild the simulation model and scenario using different tools. It might be great to simulate your system progressively from low-level specific algorithm to high fidelity system integration to reduce the risk and reduce the development time. Let's discuss how to model a system with different levels of fidelity to better focus on the associated algorithm design. At the early stage of application development, to focus on the task scheduling of the robot application, uh, your system can be modeled using a simplified motion model block or the say joint space motion model. You then quickly iterate your prototype design of your application. The MATLAB function block in the left will do the task scheduling. We don't play much attention. We don't pay attention much for grasping modeling at this stage. Later on, this motion model in the right can be upgraded with more accurate modeling of the system dynamics. After the task scheduling has been designed and verified with a simple motion model iteratively, we then add a controller for the robot, such as sorry, a more complex and manipulated dynamics model that takes the joint torques and gripper commands and a joint space controller that returns the joint torques given desired under current manipulator states. The rest of the parts remains same with the previous. We have designed the task scheduling and the controller now. Then we can add more high fidelity robot models as well as the environment models using Simscape multibody. The main difference from the previous model is the plant model. This plant model incorporates the dynamics. The plan model incorporates the dynamics with the built-in joint limits and contact modeling. This step adds simulation accuracy at the cost of modeling complexity and simulation speed. Next is autonomous algorithm design. So it's the brain of the autonomous system, I would say. So it mainly consists of three parts: the perception, the planning and decision, and control. So before going to the, if you have any question, please feel free to post it in the chat. Now, what does autonomy mean? Let's consider an example. Autonomy for UAV involves the technology components of perception, planning and decision and controls. Now, what does it look like? Okay, we have a UAV at a given starting location and it needs to navigate through its surrounding environment to get to a target endpoint. So the UAV will need to perceive and understand its own location as well as what's around the UAV itself. The UAV will then plan an optimized path through the surrounding obstacles. Then it will receive a control command to fly and follow the planned path. Let's break down to the autonomous technology components. First, for perception, this really involved self-awareness and situational awareness. For self-awareness, the UAV needs to understand where it is during its flight, in other words, the localization. Sensor fusion and tracking toolbox is an add-on product that provides sensor models such as IMU and GPS. And it can be used to design localization algorithms that fuse data from multiple sensor sources. You can also simulate and generate synthetic data from virtual sensors to test your algorithms in various scenarios, even including what if cases such as the events where the sensors fail during a flight. Simultaneous localization and mapping, or the SLAM algorithms, is often used to build maps and localize the UAV at the same time. Navigation Toolbox from MathWorks provides the capabilities to implement multi-sensor SLAM algorithms with interactive tools to design, modify, and analyze your SLAM solutions. There is an interactive SLAM map builder app as well. On the side of situational awareness, this is necessary for the UAV to recognize and understand its environment in which it is flying. This involves processing image data from the camera sensors as well as the um, this involves processing image data from the camera sensors as well as the point cloud data from the LiDARs, and typically also includes using deep learning techniques to recognize and identify the objects and or terrain elements. There are examples available to use which identifies and detects the pedestrians in a video. And finally, sensor calibration is a typical challenge when I think there were some videos and it was not playing. I don't know. Okay. Um, Sensor calibration. It's a typical challenge when fusing the LiDAR and camera outputs together to accurately interpret the objects in a scene. The LiDAR toolbox provides capabilities and interactive apps to estimate rigid transformation between LiDAR sensor and camera. Moving on to the planning and decision. This encompasses the motion planning for the UAV. Now, simpler side, UAV Toolbox provides methods to define UAV missions through waypoint following, orbit following, and customizable path planning algorithm. This is helpful when there is a predefined path that the UAV will fly so that you can quickly define this path with the waypoints and simulate the mission. For more advanced UAV path planning, you can use the path planning algorithms provided in navigation toolbox such as RRT, RRT star, and these algorithms, there are also metric tools to evaluate whether the path is valid and has proper obstacle clearance or smoothness. You can design these planning and decision algorithms within MATLAB and Simulink ecosystem depending on what type of motion planning is needed. Now let's consider the control part. Recently, there is an increase in research and application of advanced controls such as model predictive controls, reinforcement learning for UAV trajectory planning and tracking. These advanced control algorithms benefit from model-based design process by being able to incorporate the UAV model simulations. These advanced controls are applied for optimization of generating shortest path or safe collision-free trajectories, minimizing energy consumption and other aspects. Add-on products such as Model Predictive Control Toolbox, Reinforcement Learning Toolbox. It includes examples such as the quad rotor UAV using non-linear model predictive controls for trajectory tracking. It also includes training a controller using reinforcement learning with a Simulink plan model as a training environment. Now let's move on to the verification and validation. It is a second major topic of today's session. First, let's see how the verification and validation is done for a UAV. After the demo, we will have a look at the various MathWorks solutions for verification and validation. After building the UAV model, After building the UAV model and designing the autonomous algorithm, verification and validation is a critical step to evaluate whether you have designed correctly according to the requirements and to test the design to check that there are no errors. This includes requirement traceability that allow you to link specific requirements to components of the model as well as test cases to ensure that the model is associated to the requirements and that the requirements are implemented in the model. Test management and automation of test execution can be done with a Simulink test where you can define your test cases and design test scenarios through the interactive tools, automate execution of the many test cases required, and automatically evaluate the results based on the defined pass or fail criteria. Evaluating the completeness of your test is also important. You can calculate the metrics such as model coverage. You can also check that you are exercising all the portions of your models within the test cases, as well as the capability to check that the model complies to specific rules. These verification and validation tasks are especially important for certification workflows such as DO 178C, ISO 26262, and it's necessary that the applicable you need to use the qualifiable tools also for the same. It is an example of testing the UAV. It is this example provides a step through verification and validation activities within a UAV package delivery example. In this example, you can examine how requirements are linked to the model components and test cases using Simulink requirements and view the metrics for allocated requirements to ensure the modeling is complete. This we have already discussed. And this video shows the testing part. So it uses the Simulink test tool and it is a test manager window. So the test manager is used to configure the automated testing and evaluating of the results. An interface shows the overview of the requirements allocation along with the test results, which includes verification status in which green and red bars indicate the passing or failing. Now let's consider what are the solutions, MathWorks solutions for verification and validations. First one is requirement toolbox. This we have already discussed, so I'm skipping that one. Next is Simulink fault analyzer. With Simulink fault analyzer, you can model complex fault behavior and trigger conditions without modifying your design. You can manage the faults across Simulink, Simscape, and System Composer. You can also simulate faults, explore them using design studies, and analyze the fault effects. You can also perform safety analysis while leveraging the simulations. So the SFA is a workflow-based solution to help the engineers working on safety-critical systems ensure their safety requirements are valid and their designs are robust. Say, for example, I think for ISO 262, ASIL D level and all the fault injection test is necessary. Next is Simulink check. So with Simulink check, you can analyze your model to verify that it complies to the industry standards and modeling guidelines. The checks are provided for industry standards and guidelines used in the aerospace, automotive, medical, and other industries to automate manual steps to achieve the compliance. Simulink check provides dashboards to measure design, completeness, and quality. The model testing dashboard can access the completeness of your requirement-based testing to comply with the standards such as ISO 262, DO 178C. Simulink check the metrics, the dashboard consolidates the metrics from different sources to assess the status and quality of the design. Simulink check can analyze a model for patterns which could be refactored to reduce the design complexity and improve usability. Duplicate design elements or clones, often caused by copying or pasting, can cause error to propagate across a design. So this tool can detect the clones and then automatically refactor the model to replace the clones by a reusable library to improve the maintainability. Next is Simulink test. So it helps you to develop, manage, and execute simulation-based test. So it offers a test manager for organizing, executing, and reporting tests and test results. Uh, Next is Simulink coverage. So it helps you to measure the test coverage in models and generated code. The coverage analysis is performed during simulation of Simulink stateflow, C++, S functions, and MATLAB functions in the design. You can use the missing coverage data to find the gaps in testing, missing requirements, unintended functionality, or dead logic. You can also perform coverage. I have already mentioned that you can perform the coverage analysis for C++ code. Then software in the loop and the processor in the loop simulations to identify untested portions of the generated code prior to software integration testing. Any part of the design or the code that is not covered by testing is highlighted in red. You can see in the third part. So this has some uncovered blocks inside that. Interactive coverage reports are created that allow you to document and navigate through the design. Next is Simulink Design Verifier. SLDV. It uses formal methods to identify hidden design errors in the models. It helps you to generate test vectors to analyze missing coverage and formally verify that the design meets the functional requirements. So it looks for the dead logic, array access violations, division by 0. For each design error or the requirement violation, it generates a Simulink test case for debugging. It also generates test vectors to analyze the missing model and generated code coverage. The test vector drive your model to satisfy condition decision, modified condition decision like MCDC, and custom coverage objectives. SLEV can also perform static analysis on your design to formally prove that a requirement will always be met. Next tool is the Simulink real time. It helps in rapid prototyping and hardware in the loop testing. You can create, control, and instrument real time applications that run on speed code real-time target computers directly from your Simulink models and with the MATLAB API and App Designer. If you are interested to know more about the rapid control prototyping, or if you're looking for solutions to do hardware in the loop, please contact CES. So next tool is the qualification tools like IEC certification kit and the DO qualification kit. So it will help you to qualify the tools to meet the standards such as ISO 262, DO 178C, IEC 61508, and other related standards. So you can see the examples of the companies who use model-based design for applications that needed to meet the highest classification of ISO 262, DO 178C standards. We can also support you in setting the MATLAB consultation services for establishing DO 178C or ISO 262 workflows. This slide shows the Simulink and supported products for flight code certification of like a DO 178, DO 331, and related standards. We have a Simulink test, Simulink check, Simulink coverage, embedded coder, Simulink code inspector, polyspace, then this SLDV, Simulink coverage, Simulink test, etc. for that. For the standards like ISO 262 and IEC 61508, it is mandatory that the tools used for software development should also be qualified. In simple terms, the tools used for the product development do not introduce any bugs or errors to the system under development. So you can see that the listed tools are qualified already. It won't introduce any errors or bugs to your design. This this is a summary of the V&V workflow. So from requirements to mill, sill, pill, and hill. So the customer benefit is that we now have a complete product stack that fully support V&V workflows, starting from requirements traceability to hardware in the loop. This slide shows the product, the solutions for the complete V&V workflow. Next is a 3D scenario simulation. So this is a major cost saving phase in the development of autonomous system development. It's nothing but the 3D scenario simulations. So it allows the simulation and visualization of the dynamic system in a photorealistic 3D environment using pre-built scenes of indoor and outdoor environments. There are various methods to perform integrated simulations. Some new capabilities provided by the UAV toolbox include cuboid simulation environment, that include cuboid simulation environment as well as the co-simulation with the Unreal Engine simulator. Again, it's important to select the appropriate method depending on your task or the stage of the development process. The cuboid simulations are beneficial in the early stages to quickly define the scenarios and perform investigations for autonomous algorithms. Also, it is a powerful tool for developing localization, path planning, and obstacle avoidance algorithms. It allows you to perform closed loop simulations using sensor models for INS, GPS, and LiDAR. From 2021 version of MATLAB, from 2021 onwards, the capability to add weather effects to the photorealistic 3D simulations with the Unreal Engine is present. You can add effects such as rain or adjust the position of the sun, which affect the camera sensor data. So you can perform virtual testing of the perception algorithms in various weather scenarios. So just to add that 2024B is released recently, and don't forget to check out what's new in 2024B. The integrated closed loop simulations with the sensor models opens up opportunities to investigate and develop autonomous applications without real world data by allowing the use of synthetic sensor and data from simulations. One use case is for building a 3D map using simulated LiDAR point cloud data. By executing the photorealistic 3D simulation, we can obtain synthetic point cloud data from the LiDAR model. And next is creating 3D scenes for UAV simulations. For the 3D photorealistic simulations with Unreal Engine, UAV Toolbox provides a city scene by default to simulate UAV missions in an urban environment. Customizing scenes is also possible, and Roadrunner is a is an interesting app for that. It provides interactive tool and capabilities to design 3D scenes, which can be used for the Unreal Engine simulations and also for a variety of other simulators and gaming engines such as Unity. You can also use the Roadrunner Asset Library, which offers a library of 3D models that can be applied to the scenes. You can then import the custom scenes to be used in the 3D Unreal Engine simulations. The next one is the Connect to Robot. We have a variety of tools available for that, and few are listed in the slide. We are again considering the robotic example that we have I have shown in the platform design part. So the middleware such as ROS enables the communication of data in the distributed applications. Algorithm components can be prototyped and evaluated by ROS network connection to external simulators or hardwares. Your robot algorithms can be generated as a standalone ROS node into a real robot hardware. This can speed up the development process and remove the manual implementation errors. In here, we generate the ROS node onto an NVIDIA Jetson board. The next two examples are for more industrial setting, like one for the warehouse pick and place application, and the other for parallel robot pick and place using the same reference workflow. In here, the robot sorts and detect the objects onto the shelves. Robotic system toolbox, model predictive control toolbox, and optimization toolbox are used to generate optimized collision-free trajectories for the manipulator to follow. Stateflow is used to schedule the high-level task and step from the task to task in this example. You can also you can apply the same workflow for the Delta robot to sort out different types of bottles on the conveyor belt and placing them on a predetermined positions. The feature used here include a Simscape multi-body integration for rigid body tree representation, motion planner, the trajectory generation with the customizable velocity profiles, and inverse kinematics. Next is the implementation to hardware. For automatic code generation, MathWorks offers a wide range of coders. You can generate the code for use in the applications such as signal processing, industrial robots, autonomous system, embedded vision, and deep learning. You can generate C, C++, CUDA, Verilog, VHDL, and PLC code, or generate code for the middleware architecture and standards such as AutoSAR or DDS. To qualify your code for certification, verify it against standards such as ISO 262 or DO 178C. Simulink real-time and speed code take you from simulation to rapid control prototyping and hardware in the loop. So in summary, we have discussed various stages of autonomous system development with a focus on system engineering and verification and validation. MBSE and hence the model-based design will allow fast iterations and enables the use of simulations. We also discussed reference workflow examples for developing autonomous system applications. So, MathWorks offers the end-to-end workflow for the autonomous system development. So next is the resources to get started. Please visit our product web pages on the MathWorks website and download a trial to check out the reference examples. We have the robotics and autonomous system discovery page, user stories and videos for further information. We also have the hardware support page from in MathWorks website, and it provides resources to source, purchase, and configure integrated hardware solutions with MATLAB and Simulink. MathWorks also offers consulting services. So the MathWorks consultants are experts in MATLAB, Simulink, and model-based design. So they offer consultation services in the field of verification, validation, and certification of AI-enabled system for aerospace, for early verification and validation with the model-based design, MBD for production, real-time embedded systems, model-based MBD process assessment and maturity framework, process establishment of MBD, DO 178C certification and advisory service, ISO 262 process deployment, advisory service, to name a few. This is about the support mechanism of MathWorks. They provide support in different ways like a technical support, application engineering, pilot engineering, training, and consulting. So finally, this is, as mentioned before, this is the first in a series of webinar for autonomous system development. So we have two more webinars in this series. The autonomous system design and dynamics modeling from the desktop environment to hardware in the loop, software in the loop, processor in the loop setups. It will take place on 26th November. And the third in the series, autonomous system localization, planning, sensor fusion, and control from algorithm to hardware development will be taking place in 12th December. We also have some live events coming up. The first one is the MATLAB user group conference, which will be taking place on 10th of October at Warner Brothers Hotel Abu Dhabi. And we also have a live workshop on 14th October 2024 at Adnac Center Abu Dhabi in the IROS 2024 show.